Alright, in the previous video I had said that I would show you how to better incorporate the reaction time. So I'm going to do that in this video. I've actually already made the change that I wanted to make, but I want to step you through it a little bit. So I'm going to make use of an if statement, and it looks really intimidating, but it's not so bad. So let's just start off by looking at it a little bit here. So an if statement has several key inputs that you need. The first one is the condition. So we have some sort of a condition. If this is true. So we're looking for, is it true? Whoa, not sure what just happened there. Hold on a second. Alright, so the first thing we're looking at is what is the condition? And this is what will be tested to see, is it true or is it false? And if it's true, we have action 1. And if it's false, we have, so this is for true, and if it's false, we have action 2, which is for if it's false. Now, we can actually make it a lot more complicated than this, but this is the most basic formulation of an if statement. So to give you an example, you could have like if the stoplight is red. So you'd have like if red, stop, or go. I don't know what this is doing. I'll just go with it. So if you have red, stop. So this is, if this is true, you stop. And if this is false, you go. So let's look at the formula that I put in here. So this first part is my test. Okay? And I'm going to see, is this true? So D3 is the time. It's the time at this moment. That's what this part is. And if this time is less than or equal to the reaction time, that's B9, and I'm going to use money symbols so that when I copy and paste it, there's no changing of the reference. It's always going to point to this cell. Whereas D3, that's going to change. So on the line under it, whoops, not what I wanted to do. So I want this to be B9. Oops. Okay. So if I look at the line under it, you can see it's D4, and the line under that, it's D5, but B9 stays exactly the same all the time. So this is my test. When I'm under this, then we just keep it the same, and that's this true part here. So if this statement is true, I just enter in that we're going to use B3, whatever is in B3, always whatever is in B3, and that happens to be 30 meters per second. If the statement, however, is false, so in other words, if the current time is not less than the reaction time, then we're going to start accelerating. And that's what this statement is here. And this is just the statement that we had used previously if we want to update the velocity with respect to the acceleration. So this is the previous velocity, E2, that's the velocity right above it, plus V1 is the time increment times B4, which is the acceleration. So in other words, the change in the velocity. And then I just click and drag that all the way down, and you can see that it follows through. Now nothing changed because I haven't changed any of the parameters, but I can go in here and I can say, well, what if the reaction time is 0.2? And you can see that now the car 1's velocity actually diminishes much more rapidly than it had previously. If I make it 0.5, you can see that it's no longer diminishing as rapidly. But we should see that there's a bit of a problem here because car 1 is still going faster than car 2, even though their positions are almost right on top of each other. So I'm going to move these back down to 25 just to give us an example where we're talking about 55 miles per hour, maybe close to 60 miles per hour. And the other thing that's nice about this is that I can quickly and easily change my time incrementation. So when I do this, you can see that I stay at 25 meters per second for more cells, but it still switches and starts accelerating when I get to 0.5 seconds. So I'm going to go ahead and change this back. I don't think it really makes much of a difference. After 1 second we're at 23 and so on. What I am going to do is I am going to extend this whole thing down a little bit more, and then we'll look at some graphs again. Okay. Let's just click and drag this for, let's say, 4 seconds or something. 3.7 seems pretty good. So what I'm going to do is I'm going to do a graph just like I did previously, with the time on the x-axis and the positions on the y-axis, and we'll see what happens. Obviously, we can get really, really slow if we continue this on for too long. And we can also see that car 1's position, at least in this case, is exceeding car 2's. But we're just going to make it a little bit easier by making graphs. So I'm going to go to Insert, Chart. Whoops, I don't want that whole thing there. So I'm just going to highlight this entire column. What this allows me to do is, after the fact, if I need more cells, if I need to continue time for longer, it's automatically going to graph all of that stuff. So I'm just going to go Insert, Chart, and I want to add some more ranges. So we'll add another range, and we'll add both of those columns. And now we should get, if we change this to a scatter plot, the plot that we like. And after adding in the labels, we get a nice graph. And so I insert this, and we should be able to resize this a little bit. Oops, don't want to encroach too much over there. Okay, so now we get this nice graph that should show us what's going on. And if we look at it carefully, we can see that car 1 actually runs into and then through car 2 in this time. So this is a huge problem, because even if car 1 accelerates at the same rate that car 2 accelerates, this is showing us that it's not going to work out if we react after 0.5 seconds have passed, because they're honestly just too close to each other at only 5 meters apart. If we expand this out to 10 meters, which is closer to what I had in what I saw, there's about 10 meters between them, they're getting awfully close to each other. I can change this so that the time increments are a little bit longer, and you can see that they ultimately do collide with each other once again. The hope would be that sometime over this range we get maybe a slightly larger acceleration from that first car, which prevents them from running into each other. So that would be nice, but it's not necessarily always going to be the case. And you could have, let's say, a slightly distracted driver, because this is honestly not that unusual to have a reaction time of about 0.5 seconds in a situation like this. You might reasonably get down to about 0.3, which certainly makes it possible. Whoops, that's not a good idea. Which certainly makes it more possible to avoid an accident, but not guaranteed by any means, if you have a quick reaction time. But let's say that you're slightly distracted, and this reaction time goes up to about 0.8 seconds. Now you're going to have to really hit the brakes quite a bit in order to avoid any sort of a collision, which it looks like the closest point is somewhere in here after about 3 seconds of travel. And your reaction time took you to about here. If you're even more distracted, let's say that you're texting or you're turning around or something like that, and you miss by about 1.2 seconds it takes you, then we really need to slam on the brakes, and even that might not be enough, because we can see that there's basically an intersection here. So it would need to be close to maxing out the brakes in order to miss each other by more than about a meter or so. So hopefully you can see the utility of this. We can just go through and we can change all sorts of different things, time incrementation and everything like that. Obviously our model does break down a little bit because it's unlikely that this car is going to go backwards. The other thing is that you could add in another car. What if there's a car behind our car number 1? Because that car would then have to accelerate even more rapidly in order to make this situation work out. So that's actually what I'm going to have you guys do. You've already gotten the assignment, and I just want you to make that third column then, that third set of columns for velocity and position of the third car.